this section of the course, we're generally looking for a relationship between two variables. The one exception was chi-square goodness of fit, where we had one categorical variable. But when we have two variables and we wonder if they're related, the test we're going to choose depends on the kind of data we've got. So if we have two categorical variables, we'll use the chi-square that we talked about in chapter 26. Or in the special case where we have a 2x2 table, so two groups compared on a percent, we could also use the two sample z-test. When we have two quantitative variables, we'll use correlation. If we simply want to see the nature of the relationship, is it positive, is it negative, is it strong, is it weak? That was chapter 7, and now we're shifting to regression. Regression is what we use when we have two quantitative variables and we want to go beyond what is the nature of the relationship, positive, negative, strong, weak, and we want to predict one from another, or we want to see the rate of change. How is the response changing as our predictor changes? So the linear regression model looks like this. Y equals b0 plus b1 times x. So you maybe in high school used y equals mx plus b. This is exactly the same thing, only with different letters. And the reason we use different letters is because often we don't want to stop with just one predictor. We do multiple regression, and then if we use b's, we could just keep on going. Y equals b0 plus b1 times the first predictor plus b2 times the second predictor plus and on and on and on for as many predictors as you had. So that's the reason we switched to b's. So what are all these different things? Well, y is the response, that's what we are predicting. X is the predictor, that's what we are using to predict. B0 is the intercept. The intercept is the value of y when x is 0. If x was 0, 0 times b1, that drops out. So if x is 0, y is equal to the intercept. So it tells us the value of the response when our predictor is 0. And then b1 is the slope. That's the rate of change. That tells us how much y changes for a given change in x. And the simplest one is just to increase x by 1. If we increase x by 1, say from 0 to 1 or 1 to 2 or whatever, if we increase x by 1, then y will change by the slope. Y will change by the slope. So that's what each of these things are. If we want to use this to make a prediction, all we do is plug in the value for x that we're interested in predicting for and see what value y pops out on the other side. That's how we make a prediction. How do we decide if our regression model fits well? Well, we have two measures. We're going to go through this quickly and then we'll go through an example. Our two measures of fit are the standard error of the line and r squared. Standard error of the line and r squared. So first you have to think, what would make a good fit? How would we know if a regression line fits the data well? Well, we've got that, or we've got that. So in this case, a line fits the data much better. Okay, so we need measures to tell us how well does a line fit the data. So the standard error of the line is called a variety of different things in different packages, but is always by r squared. So if you can find r squared in output, the standard error of the line is right by it. It may not be called the standard error of the line like in StatCrunch. It's not called the standard error of the line, but it's always right by it. So the standard error of the line is just like it sounds. Standard error is a measure of spread. So the standard error of the line is a measure of spread around the line. In this case, there's a lot of spread around the line. The standard error would be big. Here there's very little spread around the line. So this would have a small standard error. This would have a big standard error. The biggest the standard error can get is the standard deviation of our response. So you can compare the standard error of the line to the standard deviation of y to see how well you're doing. If it's close, in a case like this, there's a lot of random scatter, so the standard error of the line, the spread around the line, would be similar to the standard deviation, the spread around the mean. In a case like this, the spread around the line is very teeny tiny, and it would be very small compared to the standard deviation of y, and so you'd know you're doing really well. So the distance of points to the line also has a normal distribution. So if we were to draw bands on either side of the line, so if you remember the normal distribution, we had 68% of observations in here, 95% in here, and 99.7% in here. Now instead of drawing lines around the mean, we draw lines or bands around the regression line. So if that was a standard error, we draw a standard error on either side of the regression line, and we'd catch 68% of our data, and draw a line again, and we'd catch 95%, and so on. So it gives us an idea of how far these points, these data points, our observed sample data points, are falling from the line. So standard error of the line is spread around the line, the distance of points to the line. The distance of points to the line has a normal distribution with a standard deviation equal to this. Then R squared is the percent of the variation in our response explained by our predictor. So how much of what's going on in our response is explained by our predictor? Are we doing a really good job of explaining what's going on in Y by using X or not? In a case like this, we're not doing a great job, because if you pick a certain X, there's a wide range of what Y's could be. So we are not doing a good job. The X is not explaining a lot of what's going on in Y. In this case, if we know X, we have a really good idea of what Y is. So this would be a low R squared. This would be a high R squared. R squared ranges from 0 to 100% because 100% is a percent. R squared of 0 means that X tells you absolutely nothing about Y. It's completely and totally useless. R squared of 100% says that all your points are on a line. If you know X, you know Y perfectly. So these are our two measures of fit, standard error to line and R squared. A few things we're going to look at in a graph to see if we've got problems with our linear regression model. We always make assumptions with statistics. And so some of our assumptions, of course, are if we've got linear regression, we have to have a line. So here are some of the things we're going to look for in our graph for problems. Do we have a curve instead of a line? Do we have uneven spread, that the points are growing as X grows, or do we have outliers, points that just don't fit the pattern? And there are various solutions for each of those. For a curve or uneven spread, it usually involves transforming Y. So taking every Y value and changing it, either the square root of Y or the natural log of Y, and those will help with both of those problems. Outliers, well, outliers always pull the line toward itself. So instead of a line like this, it would pull the line toward the outlier. So we usually do the analysis with and without the outlier and see what effect it has. So these are some problems, some graphs that suggest that we've got problems with our linear regression model, and we need to think about how to fix those problems. Okay, now an example. So here we are using the amount of chocolate eaten in a country to predict the number of Nobel prizes that country has won. So the Nobel prizes, obviously countries with a bigger population can win more. So that is the number of Nobel prizes per 100,000 citizens. And the chocolate eaten is the kilograms per person per year. So how many kilograms on average do people in that country eat of chocolate? So first, do we have two quantitative variables? We need two quantitative variables. We do. The amount of chocolate eaten is quantitative, and the number of Nobel prizes won is quantitative. Circle the regression equation. Well, if you go to StatCrunch output, our regression equation is right here. Nobel prizes won equals minus 3.4 plus 2.53 times the kilograms of chocolate eaten. So we would circle that regression equation right there. What is the predictor? What are we using to predict? Well, we're using the amount of chocolate eaten to predict the Nobel Prizes won. So our predictor is chocolate eaten, response is the number of Nobel Prizes won. What about intercept and slope? The intercept is minus 3.4. We can either pluck it out of the regression equation, or the intercept is right there, minus 3.4, minus 3.395964, minus 3.4. So remember, the intercept tells us the value of y when x is 0. So if a country ate 0 chocolate, no chocolate at all on average, we would expect them to win minus 3.4 Nobel Prizes. Well, obviously that's a nonsense prediction because a country can't win fewer than 0 Nobel Prizes. And the reason it's a ridiculous prediction is that we are extrapolating at a level of 0 chocolate eaten. So we've got 2, 4, 6, 8, 10, 12. 0 is outside our range of the amount of chocolate eaten. No country, if they're going to be a happy country, will not eat any chocolate on average. And so we shouldn't be predicting there. That's extrapolation, predicting outside of our range of x's. In this case, we've got x's from about 1 to 12, and so we shouldn't predict less than 1 or more than 12. The slope, we can either pick it up out of the regression equation or down here with the slope, 2.53. That tells us the rate of change, and all this is written on your filled-in handout, the rate of change. So as a country on average eats 1 additional kilogram of chocolate, on average, the number of Nobel Prizes won is going to go up by 2.53 on average. As x goes up by 1, kilograms of chocolate goes up by 1, the Nobel Prizes goes up on average by 2.53 prizes won. So the slope tells us the rate of change. As we increase the kilograms of chocolate, what happens to the number of Nobel Prizes won? Well, if we increase this by 1, that goes up by 2.53. If we want to make a prediction, if we want to predict the number of Nobel Prizes for a country that eats 6 kilograms of chocolate per year, well, to make a prediction, we take our regression equation, plug in 6 for the kilograms of chocolate, multiply 6 by 2.53, and then subtract 3.4, and we would get about 11.78. So approximately 12. If a country on average eats 6 kilograms of chocolate per year, then we expect they would win about 12 Nobel Prizes. Okay, measures of fit. Measures of fit, the standard error of the line. Now in StatCrunch, the standard error of the line is called the estimate of error standard deviation. And that's because it's the standard deviation of the error, the standard deviation of the difference between what we actually observed and what we predicted would happen. That's the error prediction versus what actually happened. So that is 6.39, 6.39. So remember, that gives us a measure of spread around the line. How far are these points falling from the line? And the distance that points fall from the line has that normal distribution. So we can use the 68, 95, 99.7 rule to figure out the ranges in which we'd expect to find these countries. So let's see, here's 0, here's 5. So if we add and subtract about 6.39 above and below our regression line, we're going to catch about 68% of our countries. About 68% of our countries, the number of Nobel Prizes they win is going to be within 6.39 of what we predicted, either above or below. And then 68, 95, 99.7. So 95% of our countries are going to have a number of Nobel Prizes won within about 2 of these. So 12.8, about 13 Nobel Prizes of what we predicted. So if we draw a band of plus or minus 13, 2 standard errors, we'll catch about 95% of countries. The standard deviation of Nobel Prizes was 10.22. So if we looked at the standard deviation just of that all by itself, that was 10.22. So we've decreased the spread quite a bit from 10.22 to 6.39. So this is a pretty good fit, It's not great, but it's pretty good. And then the next question, what percent of the variation in the number of Nobel Prizes won is explained by how much chocolate the citizens of that country eat? Is chocolate consumption a good predictor of the number of Nobel Prizes won? Well, the percent of the variation in y that's explained by x, that is the definition of r squared. And that's a definition you should know, because there are a number of newspaper articles and journal articles that don't say actually r squared, but stay and said the percent of the variation in our response that was explained by the predictor. So the percent of the variation, the percent of what's going on with Nobel Prizes explained by chocolate eating is r squared, and that is about 63%, 62.7%. So think, percents range from 0 to 100%. So 63%, well, that's more than half, so that's pretty good, right? So if we said 40 to 60 was sort of a moderate fit, then we're in the pretty good range. So 63% of what's going on in Nobel Prizes is explained by chocolate eaten. So that's a pretty good fit. Does the graph suggest any concerns about using the linear regression model? Well, to me it looks very linear, so that's good. Unfortunately, it looks like the spread is growing, so that's something of a problem. And there are some possible outliers. There's this country that won a whole lot of Nobel Prizes, and this one that won quite a few less than we would have expected, but mainly this one right here. So for both of those cases, we could try a transformation. The natural log is one that's used a lot in biology. So if we took the natural log of Nobel Prizes won and tried to predict that from chocolate eating instead of the actual number of Nobel Prizes won, I have that graph in your notes, and it looks better. The problem, of course, is that then you're predicting the log of the number of Nobel Prizes instead of the actual number of Nobel Prizes. So to get it back in the original units, you'd have to exponentiate it. Okay, so that is everything we talked about with that, going through an example. And then finally, we saw this association between the amount of chocolate eaten and the number of Nobel Prizes, right? There is a reasonably strong association between those things. So can a country increase the number of Nobel Prizes they win by increasing the amount of chocolate that people in their country eat? Well, probably not. There are some other explanations besides causation for a relationship between two quantitative variables. One is common response. That's where, yes, two variables are related, so x and y are associated, but there's this variable z down here that is causing a change in x and causing a change in y. So my husband told me just yesterday that people with bigger ears have a lot more knowledge. So there is an association between people with big ears and having a lot of knowledge. So the question is if we can all stretch our ears a little bit, if we'll gain knowledge. But I had my doubts, and he admitted yes. It's just that people who are older have bigger ears. And so the true lurking variable is age. As people get older, their ears get bigger, and as people get older, they gain more knowledge. So that is common response. Then the confounding is where the effects of two variables are completely mixed up with each other. And we saw that in the example of cavities and age and fluoride. So we were looking for a relationship then between, is there a relationship between less fluoride and more cavities? But the very kids who had less fluoride were also older. So those effects were mixed up with each other. It was the same kids that were older and had less fluoride. So we had no idea what caused the additional cavities. Was it the fact that they were older? Was it the fact that they had less fluoride? Was it something else entirely? Was it both? But those effects were mixed up with each other. So confounding is when you have the effects of things mixed up. That often happens when you have a study and you start out with groups that are not the same. So if you have a new treatment and you want to give it to one group and a placebo to another, And so you have two groups of patients, but one group of patients is sicker than the other. They're not starting out the same. Well, then the effect of drug is mixed up with the effect of the sickness of the original group, of which group they fell in. Okay, so in conclusion, linear regression is used when we have two quantitative or categorical quantitative variables, and we either want to find out the rate of change. If we want to know the rate of change, we're going to use the what? Intercept or slope? The slope. Or we want to make a prediction. No matter how strong the relationship is, though, even if R squared is 100%, we must be careful about claiming that a change in one variable is causing a change in the other. It could easily be common response or confounding.